This is where we stopped. Okay. So last time we talked about normal operators. So this just means t commutes with t star as functions from v to v. These are the same. Okay, so that's what it means. Composition of functions. Yes. Or matrix multiplication if you're discussing matrices. So this is and so for example, Hermitian, okay, which are t star equal t have this property, and unitary in which t star is t inverse, they both have this property. Okay? So it's easier to sometimes prove the theorem together for both these things. So that's what I will do now. Okay. And sorry, and other thing that we proved last time, or we were in the middle of proving last time, was that okay, the normal operator on Hermitian space V, let V be an eigenvalue of T, eigenvector of T, with eigenvalue lambda, okay. Then V is an eigenvector of T star. Sorry, this is taking a grip. Vector of T star with eigenvalue lambda. Okay. This is what we did, and last time we did the lab proof lambda equals 0. Okay. So then, what do we need to show? So we have that TV equals 0. So we have this, and we want to show that T star V is also equal to 0. This is a Hermitian space. So note that T star V is 0 if and only if the Hermitian product with itself is 0. Okay. But from what we did last time, okay, this is TV. This has nothing to do. I mean, this is the part where T normal is used, okay, but this is 0, okay, by hypothesis. Okay. So this proves the okay. So now lambda not equal to 0. Then so this is a trick that we have done earlier when we were doing Jordan decomposition. We consider this linear operator. Then T1V is 0. Okay, this implies by above T1 star V is 0, but T1 star is T minus lambda bar I. Okay. And so this means that TV is a T. Sorry, sorry. What am I saying? T star is no, what did I? T star minus. Oh, I'm sorry. Yeah. Go ahead. Okay. This means that T star V is lambda bar v, which is what we wanted to show. Sorry, I forgot the star and I was trying to write it slow. Yeah, this is what we need to show. Okay, so now, okay, so what we want to prove, let me just state the theorem that we want to prove. But we have to prove, a weaker lemma before it. But it'll become, so if I state the theorem and at least I'll discuss why we would need to worry about some lemma. So it'll become.
Hello, sir.
Yeah.
Sir, in this proof, if we did not consider separately the case of lambda equal to 0 or not equal to 0, and just applied the second logic that we did, then what would have been the problem exactly? I mean, if we just consider lambda to be an eigenvalue, irrespective of whether it is 0 or not, and then we consider the map t minus lambda I, then...
Correct, but then you just get t1 star equals t star, right? If lambda is 0, but how do we conclude that we don't, we'll just get t equals t1, right?
So, but that will just be the case, right? I mean, for lambda equal to 0, but that does not create any difference.
No, it does. How will you conclude anything from it?
Oh, okay, sir.
But try to write it out. You won't be, it's a good question, but just try to write. You won't be able to,
Okay, sir. I'll think about it.
Yeah. Yeah, we could. The only thing is we have to know is that is fine. Yeah, you can. Ultimate, yes, that is okay. But you need to check the first part anyway, right? You need anyway, write it out. I'm not saying that you have to necessarily write it and break into two different cases like this and prove. Okay? I could have just called lamb in general, but even if you want to use the second half, the second paragraph's logic to solve the general problem, then you still have to understand what happens when lambda equals 0. You have to know whether what t1 star v is. Just try to write it out. It'll become.
Okay, sir, I'll think.
It's a nice question, but just, yeah. It is important when we see a proof, it is important to not go through the proof and see what each step is doing. Sometimes, there may be redundant steps. Things might be getting proved twice, with no particular advantage, right? Or, yeah. So it is important to when you see a proof, it is not only important to sort of read the proof and check the lines. It is also important to read through the proof and figure out what is being established at each stage and why is it being established at each. That's, yeah. So let me state the theorem. Then I will briefly say, then I will state a lemma, and once the theorem is there, I can explain why that lemma is required. So this is called the spectral theorem. For normal operators. Okay, so the word spectral theorem refers to some result or results which talk about eigenvalues and eigenvectors of some matrix or operator or, okay. So this is what, okay, yeah. So here is the thing. So let T be a normal operator on a Hermitian space V. Then V has an orthonormal basis consisting of eigenvalues of okay. So this is the operator version, and let me just write down the matrix version, which I will not prove, but you should be able to get the matrix version from, I mean, I will say in words, but I will not write down. Okay? But you should be able to check the details. Let A be an n by n normal matrix, meaning A star A equals A star. Then there exists an n by n unitary matrix, P star equals P star equals P inverse, such that P star AP is diagonal. Okay. So let me just, okay, so let me, I will just say in words why the matrix version is same as the operator version. Okay. You should write down the details. And in any case, Artin's book does write down why it's the same. Okay. So the operator version, we are saying that there's an orthonormal basis consisting of eigenvectors of eigenvectors of T. Okay. So that is the operator version. So with respect to that basis, now because it's eigenvectors, with respect to that basis, T will be diagonal, okay? And it's an orthonormal basis. So if you write down the change of coordinates from the given basis to orthonormal basis, it will be a unitary matrix. Okay? So with respect to some, so there is some unitary matrix P such that P inverse AP is diagonal, which is and the diagonal entries are the eigenvalues. So that's what we would get. But because P is unitary, P is P star is P inverse. So that's therefore we can write it as P star AP. That gives the matrix version from the operator version. And given the matrix version, and if you want to prove the operator version, just take a basis for V, okay, or start with any orthonormal basis for V and express T as the matrix A, then just apply this version, okay, and that will give. So these two versions are the same. Depending on the context, it's easier to use one or the other. So now, therefore, I will prove the operator version. And in the operator version, what exactly do we have to establish? We have to establish that there is an orthonormal basis. In other words, we have a basis V1, V2 up to Vn such that V2 through Vn are orthogonal. I mean, Vi is orthogonal to Vj if I is different from j. For every I and j, if I is different from j, Vi is orthogonal to Vj. That's what we have to prove. And these are eigenvalues, eigenvectors of P. So this is what we need to establish, right? So in other words, if you look at the span of V2 through Vn, that is orthogonal to the span of V1. I mean, it is true for any vector. It is just, for convenience, I'm going to consider the span of V1 and the orthogonal part to the span of V1. Okay? That's okay. So therefore, we would like, and if we want a decomposition into eigenvectors, if you recall statements about diagonalization or Jordan decomposition, we want T invariant subspaces. So in other words, we are saying that span of, I mean, if you take some suitable V1, which you have not yet identified, suitable V1, that should be T invariant. And not just that, its orthogonal complement, the perp, should also be T invariant. Okay, so we need to prove a lemma that guarantees that such a thing is possible. Okay, because that's the way we can decompose into direct sum of T invariant subspaces, and therefore, if you do this individually on the summands, we can do it for V. Recall how we did Jordan decomposition or diagonalization or those things. So the idea is to break V as to be able to write V as a direct sum of T invariant subspaces. So we need the following lemma. Let V be a Hermitian space and T an operator, T a normal operator. Sorry, we don't operator on. Okay. Let W inside V be a subspace, be a T invariant subspace. Then W perp is T star invariant subspace. Okay. So that is, if TW is inside W, then T star W perp is inside W perp. That's what this means. Okay. That is just rewriting this above sentence. That's all. So now let us use this. Let's prove this statement. Okay. So proof of lemma. So what do we want to show? We want to show that T star U is inside W perp for all U inside W perp. But what characterizes W? U such that U, W comma U is 0 for every W, little W in W. Okay. So let U be inside W. Okay. Then this is 0 for all little W inside W. That's by definition, right? So we want to show that T star U is 0 for all W inside. That's what we will show. We need to show. Okay. Note that W T star U, the product, the same thing as TW U. Okay. This is 0 since T little W is inside W. Okay. For all W inside W. Maybe I should put the quantifier here. Note that for all W inside W, this is 0. Okay. This is what proves the lemma. Okay. So this, the ability to move this T star to this side. Okay. That's a property of this. So this is a proof of the lemma. So with this, we will, now assuming T is normal, we will be able to decompose V into two subspaces, and then we will be able to build the matrix of T, or the orthogonal basis of orthonormal basis of V. So now proof of theorem. Okay. Let V1 inside V be an eigenvector of T, okay, with length of V equals 1. This is always possible. Given any eigenvector, we just divide it by its length. Okay. Eigenvector is non-zero, so it has a non-zero length because it's a Hermitian product. Okay. It is positive definitely. Okay. So it has a non-zero length, and so okay, and then you divide by that thing, we would get a vector of unit length, which is still an eigenvector. Okay. So it's an eigenvector of with unit length. Okay. Then V1 is an eigenvector of T star. So this is where we used one of the propositions. Eigenvalue is different, but that is not really. Let W be the span of V1. So then W is T star invariant. That's just rewriting the fact that V1 is an eigenvector of T1, T star. Okay. By lemma, W perp is T invariant. Okay. Notice that W is also T invariant. Because it's an eigenvector. I mean, for a single vector, the span of one single vector to be the span that subspace, one-dimensional subspace to be T invariant is equivalent to saying that that vector is an eigenvector. Okay. So this is an eigenvector for both T and T star with different eigenvalues, but that's not really relevant. It's just an eigenvector for T and T star. Therefore, both W and W perp are both T and T star invariant subspaces. That's what the previous lemma and the proposition, which we continued from last lecture, establishes. Yeah, this is okay, so W perp is T invariant, and okay, since the given Hermitian form is non-degenerate, I mean, it's positive definitely. It's going to be non-degenerate on every subspace on W, which follows since it is positive definite. V is W direct sum W perp. Okay. But this is exactly what we wanted. Okay. We have now written V as a direct sum of two T invariant subspaces. Okay. So let V2 through Vn be an dimension of W perp is less than dimension of W. It's in fact it's equal to dimension of W minus 1. Okay. So okay. T restricted to W perp. So now because it is T invariant, this is a map from W perp to itself. That's why we need to establish this T invariant part. We get a map like this. Okay. Is a normal operator. Okay. So normal operator, okay, maybe I should just say it once more. Okay. So T, I mean, what we want to show is that T restricted to W perp composed with T restricted to W perp joint equals T restricted to W perp joint with T restricted to W. This is what we want to show. Okay. But these are functions. From W perp to itself. Okay. And if you say if you want to show that two functions are equal, then it means that for every input, they give the same. Okay. Okay. So therefore, it's enough to show that T restricted to W perp of T restricted to W perp star applied to some U equals this thing being applied in the opposite direction. For all U inside W perp. This is what we need to show. But as far as elements of W or W perp is concerned, this is the same thing as, but this is the same thing as T of T star of U equals T star of T of U for all U inside W perp, which holds because it also holds on V. Since it holds for all U inside V. Okay, so just for once, let me just clarify what it means to say that T star is equal to T star. I mean, it is true for, we're just composing two functions, and then, I mean, we're just considering two functions. We want to say that they're equal. And when do we say two functions are equal? Precisely when for every input, they give the same output. That's what we just did. Okay, so this is a normal operator. Therefore, by induction on dimension, W perp, yeah.
So
Yes.
could you scroll up for a minute?
Yeah. This one or earlier? Huh?
Yeah, that's fine. I read it. Yes. No. Yeah, so you can go ahead. Yeah.
W perp has an orthonormal basis. V2 through Vn of eigenvalues of T. I mean, eigenvalues of T restricted to W perp, but they're also eigenvalues of T. W perp is a subspace of. Therefore, V1 through Vn is an orthonormal basis. Of a basis of V of eigenvalues of, is what we want. Okay. But I mean, quite often the matrix form is how most of the time we'll have to apply, which is just to say that if A is a normal matrix, then there is a unitary matrix P such that P star AP is diagonal. Okay. So the fact that it is diagonal says that the new basis consists of eigenvectors. Okay. And because P is unitary, P star is same as P inverse, and which is what we do when we want to do change of basis. Change of basis is P inverse AP. Because it's unitary, it's the same thing as P star AP. Okay, so this is the theorem for normal operators. And yeah. Okay, so now immediate corollaries. I mean, essentially, the reason why we consider normal operators is we want to prove something about Hermitian and unitary matrices. And so we just write, so we try to analyze whether that statement is true for normal operators. So let T be a Hermitian operator on the Hermitian space V. Then there exists an orthonormal basis of V consisting of eigenvectors of T, and two, the eigenvalue. Both these statements you have already proved. I'm just stating them. Eigenvalues of T are real. Both these, I mean, the first statement is the immediate corollary of the previous theorem, spectral theorem, and the second statement is something that we have proved earlier. so in matrix version, okay, let A be an n by n Hermitian matrix. Okay. Then there exists a unitary P such that P star A P is a real diagonal matrix. Okay. That is the, remember, if you have P inverse AP as diagonal, then it means that the diagonal entries are the eigenvalues, right? So here P is unitary, so P inverse AP, same thing as P star AP. So now we have P star AP, and that's a diagonal matrix. And since we already know that eigenvalues are real, we would get a real diagonal matrix. Okay. This is the sorry, I should have named it. This is the spectral theorem for Hermitian operators. Okay. And we can similarly write already two spectral theorem for unitary matrices. Okay. Suppose that U is a unitary matrix. Okay. So let U be a unitary matrix. N by N, let's say. Okay. So then there exists a unitary matrix P, such that P star U P is diagonal. You can't say anything more about the eigenvalues. In fact, eigenvalues potentially are complex. Okay. So this is the okay. So these are okay. So these are what is called what are called the spectral theorem. Okay. So it's more convenient to prove it in a common way for both normal operators. So it's typically proved like that. But the real application is the individual cases, Hermitian and unitary. Okay. And Hermitian is particularly used and also useful because it actually says the eigenvalues, the diagonal matrix is a real matrix. So this is okay. So that's the end of this chapter that I was doing on bilinear forms. Okay. It took me longer than I had planned for, but it's okay. I don't think I think you have spent. I mean, I don't think you've gone too fast or too slow for that matter. Okay, so what is the time? Okay, yeah. Okay, so now I'm going to switch to groups. I should have started this earlier, but anyway, we will do whatever is feasible in this for the rest of the semester. Okay? At least the key things we will learn. So what are they? I will give a proper definition later. Later meaning after we look at a few examples. So they are sets with a binary operator. Sorry, operation. Okay. So okay, that behaves nicely. We'll say what it means. What nicely means will become clear in the next few minutes. And then I'll give a proper definition. So the foremost example of a group is Z and the binary operation. So we will typically write like this. Okay. This is the set and this is the binary operation. Binary operation means an operation that takes the input of two things and gives some output of 1. Okay. So in other words, it's a map from, if you call the set X, then it's a map from X cross X to X. Okay. So maybe I should just clarify it once. Okay. If X is a set, and let me just for now call it star binary operation. Or maybe I should say, let X be a, okay, I'll write it like a proper definition. Let X be a set binary operation on X is a function star from X cross X to X. Okay, that's what we mean by binary. Okay. However, so this is a definition, notation. Okay. Instead of writing star of some x1, x2, okay, as we would do for functions, do ordinarily for functions. Okay, we will do what is called the infix notation. We will write x1. Okay, maybe x was not the best symbol to denote this part. Let me just call it AB. Okay, we will say A star. Okay, like the way we write plus or multiplication or, okay, that's just notational difference. Okay, let's go back to the example. Z, so plus is a function that takes two integers in this context and gives an integer. So it's a function from Z cross Z to Z. And we don't typically write plus of 3 comma 2. We just write 3 plus 2, right? Symbolic. So just the notational. This is okay. So what other property does Z plus have? Okay. So 0 plus n equals n plus 0. Okay. So first of all, plus is additive. Additive. Sorry, not additive. Sorry, associative. Okay. So that is n plus m plus p. Associativity of a binary operation means this. Okay. F of x of f of y comma z is, okay, you can associate it the other way around. This is C. This equals n plus m plus p for all m, n, p in Z. So this is what we mean by associativity. Then 0 plus n is same as n plus 0. This is same as 0 for all n in Z. Okay. So 0 is the additive identity. 0 is the identity elements. Identity element for plus. Okay, that's the, so this I'm just, yeah.
Shouldn't it be n?
Oh, sorry. Thank you. Thank you. Otherwise, it would be, thank you. Okay. And last thing is that for every n, there exists m. For every n in Z, there exists m in Z, such that n plus m, same thing as m plus n, is the same as Z. That is, take n to be, so because of this, we will to be minus 1 minus of n. So this is called additive inverse, I mean inverse. Okay, so this, inverse, for the operation plus. So this is just, okay. So these are the properties that we're going to look for in a group, in what we will call a group. Okay. A set with a binary operation that is associative, has an identity element, and every element has an inverse. So I'll make the definition proper after we see a few examples. Okay. Second example, we can do the same thing for the set of rationals with the same operation, the set of real numbers with the same operation, and the set of complex numbers with the same operation. Okay. Similar argument, similar as Z plus. Same, essentially, you can just, instead of writing wherever we write Z, we can just write replaced by the correct symbol, Q or R or C. All of these statements will go through.
Even the vector space.
Is what?
Even the linear space also.
I will come. Let me do one example at a time. Yes, I will come to everything. Yes, you're right, vector space, but I'll come to it later. Okay. Now I want to consider another group, another thing that has similar behavior, which we will denote not Q with the times symbol on top, multiplication symbol on top. Okay, so this is the set is Q minus the non-zero elements of Q. Okay, and the operation is multiplication. Okay. So again, the argument is almost similar, except associativity. So if we have some Q1, Q2 for all Q1, Q2, Q3, maybe it's called ABC. ABC inside Q, but not 0. Okay. So especially if you're writing multiplication, we won't write this dot. We will just write AB times C is A times BC. Okay. So we omit notation. If the binary operation is denoted by dot, we often omit it and write AB instead of, because see, if you just try to write these things as the definition goes, it'll be just very tedious. So at some point, once we understand what we mean, we sort of use various abbreviations. Okay. Now, what is the identity element? For all A inside Q, but not 0, A times 1 is 1 times A. This is A. And for all A inside Q, but not 0, there exists B inside Q, but not 0, such that A times B is B times A is 1. Okay. So again, so 1 is the identity element for this binary operation. Okay. And this is just reciprocal, the usual. Well, and so similarly, R minus 0 with the multiplication operation, C minus 0 with the multiplication operation. Okay. However, Z, if you do this to Z, we do not get a group. Okay, I will just say it's not a group, but I have not yet defined what a group is. But at least I'll check that its behavior is not the same thing. So for example, okay, so this operation is associative. That is okay. 1 times n is n times 1 equals n for all n in Z. That is also okay. But there exists n such that for all m inside, there exists n in Z, but not 0 in this set. Okay. There exists n in this set such that for all m in that set, okay, n times m is not equal to 1. Okay. That is no inverse.
P power n something.
Is what?
where P is prime. P power n where P is prime, that will form a group, right? Like a 2 power n, like 2, 4, 8.
Well, okay. Since you asked, you will do as an exercise. I will put this in the next week's. I mean, oh, I see. I will put. So this, okay. So I didn't say about exercise. So I'll put some exercises this week, which should sort of help you. I mean, so next week there's no quiz. It's just a midterm exam, right? So since you ask, yeah, we'll put that as. But maybe I'll postpone this particular. Okay, maybe I'll put this as an exercise. But I would like to revisit this example later, but that we will do appropriate time. That will be after midterm, probably. Okay. So I will assign, I mean, I will put some exercises this week, but that should sort of help you towards the midterm exam on the topics that I'm lecturing now. Okay. So everything that I teach up to Thursday is included in the midterm. Yeah, up to the days what Tuesday, right? Yeah, next class. But just to say, majority of it will be from the linear algebra part, not from group theory. But group theory, will, I mean, whatever I discuss today and in the next lecture will also be included. But they are elementary things. So this is, but you're right. Whatever you describe as a group, and we will revisit when we talk about morphisms, group homomorphisms. Yeah, so we talked about something that's not a group, that doesn't behave like this. Okay. So maybe then it is time to see the definition. That G, a group G. So for now, I will denote the binary operation by a dot. But sometimes the natural operation will be a plus, will be addition, and in that case we'll use group G plus. A group which is a pair, is a pair. Sorry, is a pair G comma dot, where G is a set and dot is a binary operation on G, okay, satisfying the following. Okay. First statement. So it's a binary operation. So if you take, I mean, it takes 2 elements of G and outputs an element of G. This is what we mean. This is associative. That is A, B, C. So as I said, when the operation is denoted with a dot, we often omit it in the notation, just for sake of conciseness. So this is the same thing as A, B, C. For all A, B, C inside 2, there exists an identity element, E inside G, that is, for all A inside G, A times E is E times A is A. And 3, every element has element has an inverse. An inverse. That is, for all A inside G, there exists B inside G such that AB is BA is the identity element. So this just codifies the common behavior, the part that we want to codify from the previous examples. So another another important class of more examples. Okay. So one that somebody already mentioned. What was the number here? Okay, maybe I'll still start with one since I call it more examples. Vector spaces. Let V be a vector space over some field. Okay. Then V with the plus operation, the usual vector addition. So this is vector addition. Okay. Is a group. Okay. And okay, identity element is the zero vector. Okay. And inverse element of V inside V is -1 times V. Okay. Those for every V. So vector spaces is one example. With the vector addition is one example of. Okay. We can go even further a little bit. Okay. Fix Mn. Okay. So let M n cross M be the set of, and a field of integer, positive integers. Be the set of n by m matrices over a field. Whatever field, real, complex, rationals, any other field that you're fitting. Maybe I should just call it that. Okay. Then M n plus M n times M F is a group with matrix addition. This is a special case of the previous example. Addition as the operation. Okay. Then the zero matrix is the identity element. And the inverse of a matrix A is minus A for all matrices. Okay, so this is one example. Yeah, the reason why I listed this is because we can also think of matrices as not just as the set of matrices as vector spaces, but you can also think of them as the set of linear transformations. So that's the reason why I listed this out separately. And another important class of mod groups. Okay. So let F be a field, real, complex, rational, whatever which you like, okay, and n positive integer. Okay. So I listed few important fields, groups in this thing. Okay. GL and F, the set of n by n invertible matrices. Okay. Over F. Then SL and F. Okay. Again, n by n invertible matrices with determinant 1. I mean, again, over F. Okay. So these are, so let this be this and this be this. These are groups, okay, under matrix multiplication. Okay. The identity element is In, and inverse of any inverse of a matrix A is A inverse. Okay. So this is not a linguistic play. On the one hand, we're talking about inverse of the matrix with respect to the group operation. On the other hand, we mean A inverse as it's an invertible matrix. It is just that it is not purely a word play. I mean, there are definitions, but the words are chosen so that they carry the usual meaning. Okay, it's inverse of matrix. Okay, so this is an important example. So another, okay, so one definition. A group G dot is abelian if the operation is commutative. AB equals BA for all A and B inside G. So that, if you notice, that was not part of the definition. Okay. And let us go back. So that was not stated here. It was stated that it is associative. Okay. And the rest of it is just some properties. Okay. About the existence of inverse identity element and inverse element. But now, if you put an extra condition that the operation is commutative, we call such a group an abelian group. Okay. We can look at, so all the examples that we wrote on the beginning, Z with plus operation, Q with plus operation are all of these things. Multiplication, all of these are abelian groups. Okay. So the only non-abelian group that we have seen so far is this GLN and SLN. Okay. So all the examples above, all the examples of groups discussed above, okay, except GLN and SLN are abelian groups. Okay. GLN and SLN are not abelian. If n is greater than 1, GLN and SLN are not abelian. Okay, it is easy to find what are we saying? There are 2 by 2 matrices whose 2 by 2 matrices A and B, such that AB is not equal to BA. You can easily find such examples. You can even get their determinant to be 1. Okay, that's very okay, that's not at all difficult. Okay? They don't commute is very, I mean, if you consider 2 by 2 matrices, getting a pair which don't commute with each other is it's not at all difficult. So I leave this. Okay, so find, I mean, prove it for n equals 2. And once you can prove n equals 2, you can prove for any n.
GLN is an groups over the multiplication operator, right?
Correct. Did I say matrix multiplication? I'm sorry if yeah. I said groups under matrix multiplication.
Okay.
Yeah. Multiplication, not addition. Yeah. So this is okay, so I want to introduce an important class of groups now. So let X be a set.
So, just a question, like we have a set, a binary, where a binary operation is defined. Can we find the biggest subset of that set which forms a group with that binary operation? Just as we did for the integer comma multiplication, it doesn't form a group. However, that p power n does form a group. So I think that
So
is
2 power n is not, no. 2 power n is not a group under addition. It's a group under multiplication.
Multiplication. Yeah.
Yeah, but that is not a
integer That is not a group under multiplication only. So as a subset
No, but
of that,
then
that is
the question becomes, I mean, what do you mean by can you find a larger subgroup? Do you want it for the
I
same
just,
operation or
just
some
in
other
terms of
operation?
cardinality sometimes.
No, that, I mean, if you change the operation, it could, I mean, anything can happen. So the other thing,
No,
yeah,
with same operation, but
no, but it's not the same operation, right? If you consider 2 to the n, it is not the same operation. It's not even a subset of integers, right? I mean, 2 to the minus 1 is a rational number.
2 into 2 into dot, dot, dot. No, in positive.
No, but that's not a group. I mean, what is the inverse of 2 square? I mean, 2 into 2. Yeah.
Yes, thank you.
So let X be a set. Okay. Consider, which I will write Bijx to be, the set of all functions from X to X such that F is bijective. Okay. This set is a group under composition of functions. Okay. So in other words, so what are we saying? If F from X to Y, X to X, so it is the same set, that is, okay, and G from X to X are bijective functions, bijective, then so is, let us say, let's write like this. It doesn't matter. I mean, these are universally quantified. So the right G F or FG, it's the same logical statement, is bijective. Okay. The second part requires a little bit. So this is the binary operation part. Okay. So this is, maybe I should say, this says that composition is a binary operation. On the set of bijective functions on X. That's what it's establishing. That the first sentence. Okay. So the second thing requires a little bit of checking. So please, so this is somewhat tediously verified in the textbook. So please read it. Okay. For all F, G, and H inside bijective functions from X to X, okay, F composed with G composed with H is same thing as F composed with G composed with H. Okay. So this is to be checked, okay, by on every element of X. Okay. So this, in other words, it means that F of G composed with H of X equals F composed with G. If you write out, it is this. I mean, it is sort of tautological, okay, for all X in X. That's what we maybe say two functions are the same. Okay, that they agree on all input. Okay, so this is what. So please check this. Okay, so that is. Please check this parenthetical statement. If you have some difficulty, take a look at the textbook. Okay, so this is what. So this establishes that this is a associativity. The third is what is the identity function? The identity element is, I will write like this. It's identity function on X, that is the function X goes to X on X. Okay, so then it is easy to check that. This operation is composition. Okay. And inverse element is the usual F inverse. Inverse element, inverse of F, the function F inverse. Since F is bijective, F inverse exists and it's also bijective, right? So this is okay. So this is an important class. So right now it's written somewhat abstractly. What is X? Why do okay? So okay. So I just want to give one specific situation where this comes. So in fact, so I want to just, in fact, GLN F consists of certain, not all bijective functions, certain, I mean, some special, that is some, that is, I should not probably use the word special because that may sound like SLN. Okay, certain, that is satisfying some specific property, which is that these are linear transformations. Okay. Certain bijective functions from Fn to Fn. Okay. So GLNF consists of, if you think of it as functions from Fn to Fn, they are precisely the bijective linear transformations. Okay. So this is sort of related to this general example that I just described. So it's not a new the idea of considering bijective functions from a set to itself as a group under composition is not a new idea. You have done it, which is using invertible matrices. It's just that you have not thought about it as a group or probably not as bijective functions. Okay, but I just want to say that it's not a new idea. Okay. Finally, so although it is close to time, I just want to still discuss an important subclass of this bijective functions. So suppose X is a set of n elements. Okay, that is a set of n elements, and we may as well just call them 1 through n. Then so I will explain this part again next time, but I want you to think about it. It's the set of permutations of 1 through n. Okay. Any bijective function is just is permuting those elements. F of 1 is something, f of 2 is something, and so on. They're distinct, and so it's just permuting them. This is, and this has a special name. This is called the symmetry group. Symmetry group or symmetry group. Okay, on n elements, or permutation group on n elements. Okay, and is denoted Sn. This is somewhat standard notation. So we will. So I'll stop here, but and I will revisit this bijective functions and what permutations are in the next class. Permutations form an important class of, I mean, permutation groups form an important object of study. So we will look at it at greater detail. And so are there any questions?
Sir, I had a question regarding the symmetric bilinear. Can I ask it now?
Sure.
Okay, so is there a necessary and sufficient condition for like when a W, which is subspace, is equal to W perp perp?
W equals W perp.
W perp perp, yeah.
I mean, first of all, it requires that it is not a, I mean, first of all, it requires that the form is degenerate on W, right?
So
And
W is equal to W perp perp 2 times.
Oh, 2 times.
Yeah.
I see. So that's a mistake I made in the last example, the last quiz, right? Yeah. So for every subspace W, is that what you're asking? Sorry, I didn't get your question. Are you asking a condition on W, or are you asking a condition for the form?
Yeah, sir. Like I don't know, like for both.
For both, okay. For the first question, I don't know the answer. There could be. I mean, I'm. So if the form is non-degenerate on the whole space, I think, for every W, I mean, I'm discussing finite dimensional spaces. W double perp will be equal to W. If the form is non-degenerate in the whole space. And if the form is degenerate, I mean, that means one of the eigenvalues is 0, then you can find W such that W perp is bigger than W. I mean, you could still find W where W perp is equal to W, but you can find W such that W perp is strictly bigger. Does that answer your question?
Yeah, okay, sir. Yeah.
Sir?
Yeah.
Sir, sorry to bother you with this. Like this is not content related, but I mailed you a couple times about this as well. I missed the quiz last week.
As I had clarified in an earlier email, if I will take makeup quizzes if there is a doctor's note. That's the only condition on which I take. I will accept. Yeah.
All right.
Yeah. Okay, I'll stop here.
So I tried to prove it. Okay. Thank you, sir.
Hello, sir.
Yes, go ahead.
Sir, in exam, if we are said about positive definiteness or anything like that, then we can consider it to be the symmetric form, right, by default? I mean,
correct. Exam, if I say use the words positive definite, I mean symmetric or Hermitian. Could be Hermitian, but
so same for orthogonality also, right?
Yeah.
Okay.
Yeah.